Let's start to look at some examples of surface area calculations. To begin with, let's find the area of the graph of the function z equals 2/3 x to the 3/2 power above the rectangle in the xy plane, where x is between 0 and 3 and y is between 1 and 5. So the first step is going to be to parameterize the surface. So here, we're already given the function as the graph over the xy plane, so let's parameterize it as a graph. Now remember, one option is to set x equal to u, y equal to v, and z equal to f of u and v. So 2/3 u to the 3/2. But I think it'll be easier for us to understand if we simply let x equal to x, y equal to y, and then z equals 2/3 x to the 3/2. So our parameterization phi of x and y is given by x, y, and 2/3 x to the 3/2 power. The reason I like using x and y is because here are the bounds that we'll end up using when we set up our integral. So that's step one. Step two is to find a formula for the surface area element, big DS. Since my parameters are x and y here, the formula will be the length of d phi dx crossed with d phi dy dA, which is dx dy. So we need to differentiate phi with respect to x and y, take the cross product, and take the magnitude of that cross product. So several steps. The derivative of the parameterization with respect to x is going to be 1, 0. Using the power rule here, I'll get 1x to the 1/2 power. The derivative of the parameterization with respect to y is 0, 1, 0. So now we need to take the cross product, and we save a little bit of space by just writing I, j, k. And then I need to take the determinant of this matrix. So d phi dx crossed with d phi dy is going to be I times 0 minus x to the 1/2. So minus I x to the 1/2 minus j times 0 minus 0 plus k times 1 minus 0. So in our usual notation, that'll be negative square root of x, 0, and 1. And then finally, the magnitude of that is the square root of negative the square root of x squared, which is x, plus 0, plus 1 squared, which is 1. So our surface area element, ds, is the square root of x plus 1 dx dy. And that's the end of the second step. Now let's set up the integral and evaluate it. The surface area of S will be the double integral over R of the surface area element, which is going to be the integral of the square root of x plus 1 dx dy Here it doesn't really matter whether I write dx dy or dy dx because I'm integrating over a rectangle. X goes from 0 to 3, and y goes from 1 to 5. In fact, notice that I am integrating over a rectangle. All four bounds are constants. And my integrand is the product of a function of x and a function of y, where it's just 1. The function of y is 1. So if I like, I can break this up as the integral from 1 to 5 of dy times the integral from 0 to 3 of x plus 1 to the 1/2 power dx. Now the integral from 1 to 5 dy is easy. That's just y taken from 1 to 5, which is 4. So that part's done. To do this integral requires a u substitution. If we set u equal to x plus 1, then du is dx. And also notice, when x equals 0, u equals 1. And when x equals 3, u is 3 plus 1, or 4. So translating this integral, x plus 1 to the half is going to be the same as u to the half. Dx is the same as du, but my u bounds are from 1 to 4. So I'm integrating u to the half from 1 to 4. The antiderivative of u to the half is u to the 3/2 times 2/3. This will go from u equals 1 to u equals 4. Multiplying, I get 8/3 times 4 to the 3/2 power minus 1 to the 3/2 power, which is 8/3 times 8 minus 1, and 7 times 8 is 56. So I get 56 over 3 as my surface area.